Section 15 of the Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Outline of Science, by J. Arthur Thomson. Meteorology, Part 1. The Science of the Weather. The aim of modern meteorology is to investigate the great ocean of air that surrounds our planet, and to discover the laws that govern its circulation. A complete knowledge of these laws would render possible the forecasting of the weather for considerable periods, and thereby meteorology would prove itself to be a science of the greatest value. Climatic conditions, more than anything else, limit the habitable area of the earth. Although there is probably no climate to which man cannot adapt himself, the coldest lands are either uninhabited or sparsely populated, like northern Siberia, for example. The influence of climatic conditions on race temperament is very pronounced, and has often far-reaching consequences. In the past history of the earth there have been great changes in the climate brought about by a succession of ice ages, periods when vast areas of Europe and North America lay hidden beneath great fields of ice, when the great mountain systems formed the cores of mighty glaciers, from which, after the ice ages had been succeeded by warmer periods, great rivers flowed down and fed lakes and inland seas, where now there is naught but the sand of the desert, or at most some shrunken lakes with no outlet to the sea. All this occurred, however, ages ago, and though at the present time the earth's surface shows conspicuous belts of desert, there is no definite evidence of a general drying up having occurred within historic times. In fact, in some places there is not wanting proof to the contrary. Thus, in Central Asia, desiccation does seem to be increasing, yet in the Sahara vegetation is said to be encroaching again upon the desert. Section 1. The Causes of Weather. Weather changes are the result of the general turbulence of the atmosphere. The greater the turbulence, the more profound will be the changes. The turbulence is due in the first place to the influence of the heat received from the sun, and it is increased by the effects produced by the earth's rotation and revolution, by the irregular distribution of land and water on the earth, by the variation, according to latitude, of the intensity of the incident solar heat, and also by the fact that the atmosphere, being a gas, is subject to changes of pressure and volume as well as of temperature. Although the mathematical and theoretical side of meteorology is now receiving close attention, it has been the observational side of the subject that has up to the present undergone the greatest development, and indeed it is most essential that the observation should form the basis of the theory, and that theory should conform to the facts. Therefore we find that in nearly every civilized country in the world there exists a meteorological organization, generally a government institution, whose duty it is to obtain observational records and to employ them for the preparation of forecasts and for statistical purposes. In Britain, the former Meteorological Office is now a special department of the Air Ministry. The two regions of atmosphere. Our planet is surrounded by a great ocean of air. The air itself is a mixture of gases, the chief of which, in the lower layers, are nitrogen and oxygen. Much smaller quantities of carbonic acid gas and water vapor are also present, together with the rare gas argon. In the upper layers, the composition may be different. Hydrogen and helium are both believed to be present. The latest theory is that helium predominates. So far, however, as temperature is concerned, the atmosphere is divided into two parts: a lower region in which there is a fairly rapid decrease of temperature with height, and an upper region where, as far as the limit investigated up to the present, such a condition does not prevail. The higher layer, in which there is no material change of temperature with height, we call the stratosphere. The lower layer, in which there is considerable lapse of temperature with height, we call the troposphere. The region where troposphere changes to stratosphere is generally, but not always, marked by a sudden cessation of fall of temperature. Sometimes the change is more gradual, but in almost all cases it is possible to define the level where the stratosphere commences. This level varies with the seasons and with the geographical position of a place. In our latitudes it is on the average about 7 miles above sea level. The temperature of either the stratosphere or the troposphere is of course not constant, but shows considerable variations. The point is, that in the former case temperature does not decrease with height, in the latter case it does. The belief once held that the higher we ascended, the colder it would continue to become, is therefore not true. Let us see how this astounding fact was revealed. Section 2. Sounding the upper air. Of late, a great deal of study has been given to the conditions that exist in the air above the earth, and, whenever possible, the chief stations investigate the upper air by means of balloons. Two types are used, one of which is a fairly large balloon called a registering balloon, or ballon sonde. This balloon is sent up with a small instrument called a meteorograph attached to it. The balloon, set free, rises upward until it bursts, when the meteorograph falls down to earth. The instrument is protected from injury by being enclosed in a light bamboo framework, while the remnants of the balloon fabric act as a parachute, so that the records obtained are usually recovered in good condition. A notice is attached to the instrument entitling the finder to a reward on handing the instrument in at any post office. The records made include pressure, temperature, and humidity, and the whole is contained on a small rectangular plate of silver-plated metal, not much bigger than a postage stamp. A microscope is required to enable the traces to be read with accuracy, but the results are very dependable. The other type of balloon is much smaller, usually only 18 to 24 inches in diameter when inflated, and is made of thin rubber, generally dyed some dark color to render it easily visible. The balloons are termed pilot balloons, and are sent up in considerable numbers every day at stations all over the country. They are inflated with hydrogen, and after being released, they are observed in their flight by theodolites at either one or two stations. If 2 theodolites are used, the stations chosen are separated by half a mile or more, and the length of the base line so formed affords a datum from which the balloon's position can be accurately determined. Both observers at the 2 stations take simultaneous readings every minute of the angular altitude of the balloon and of its azimuth, i.e. its horizontal angular position from the baseline, and from these readings the position of the balloon at each minute is obtained. A far more rapid method, however, is to use only one theodolite for taking the necessary position readings, and to assume that the balloon rises at a steady rate, which has been determined exponentially and found to be between 450 and 500 feet per minute for balloons of the size above mentioned. Knowing the height, and the azimuth and elevation angles, the balloon's position can be rapidly determined by the use of a slide rule. As a matter of fact, this second method is the one commonly employed at meteorological stations, on account of its expedition, for it is quite possible to have all the results worked out by the time the flight has ended. Observing the tracks of the balloons. The balloons follow curious tracks at times, especially at stations on our eastern coasts, when a sea breeze may be blowing shorewards, for the balloon in such a case will travel westwards over the land, but as it is rising at the same time, it will soon pass beyond the influence of the easterly breeze, and, if the wind above is from some westerly point, as is usually the case, the balloon will often return overhead across the station and be lost to sight far over the sea. At other times the track will form a wide sweeping arc, generally tending towards the right. Occasionally the track will be a somewhat irregular spiral. In fact, it is the exception for the track to be a straight one. This means, of course, that the wind directions at various levels in the upper air are often very different from those at the surface, and this fact is of the utmost importance to aerial transport, for an aircraft can at times reach its destination more quickly by choosing a suitable level. Astonishing facts revealed. Small as they are, these pilot balloons are often kept in view to very great heights. It is quite common for 20,000 feet, nearly 4 miles, to be reached, and half as much again has been exceeded, ere they have been lost to sight in the theodolite telescope. The larger registering balloons have reached even greater heights, for records have been obtained of the temperature and pressure up to 14 miles above the Earth's surface. And these records have a very curious story to tell us. In days gone by, it was always believed that the higher we ascended, the colder it would become, until the cold of outer space was finally reached. But this is not so. The temperature does fall off with height until a certain level is reached. But above this level, the temperature remains practically unaltered as far as registering balloons have yet penetrated. In our latitudes, this level is about 7 miles up. Over the equator it is about 10 miles, while in polar regions it is lower, being there only about 5 miles. Now this fact introduces a rather curious paradox, because if the air temperature keeps on decreasing until the level is reached where temperature ceases to fall, it means that over the equator, the temperature at a height above 10 miles must be lower than the temperature at a corresponding level over the polar regions. And this is actually the state of matters, for, notwithstanding that the surface air at the equator is much warmer than that in the polar regions, yet the temperature at the 10-mile level over the equator is about 110 degrees below 0 Fahrenheit, while over the Arctic Circle it is only about 60 degrees below 0. The existence of this level where the fall of temperature ceases means that we have to consider the regions above and below it as essentially different, and so, as we have seen, the two regions are named the stratosphere and troposphere, respectively. Within the troposphere, where the temperature decreases with height, it is possible for heated air to rise upwards because warm air is lighter than cold. But within the stratosphere this cannot take place, for when a mass of air rises the decrease of pressure causes it to expand, and the expansion lowers its temperature, so that it would become colder than the surrounding air. In other words, it would be prevented from rising. The cause of the existence of the stratosphere has not yet been fully explained, but its effects are considerable. All turbulence of the air must occur below the stratosphere, and practically all the clouds must be formed beneath it. All our storms and changes of weather must therefore take place within the limits of the troposphere. The narrow limits within which life is possible. When we take into consideration the rate of fall of temperature with height, the effect of which is forcibly demonstrated by the snow-capped mountains even in equatorial regions, it will give us food for reflection to remember that all the teeming life on our planet is rendered possible by a thin zone of air approximately 3 miles deep at the equator, and thinning out northward and southward, till it ends at the ground level in the neighborhood of the Arctic and Antarctic circles. Of the whole extent of our atmosphere, this belt or zone is all that has a temperature above freezing point. Section 3. Pressure and temperature. Atmospheric disturbances, then, have their origin in changes of temperature and pressure. Temperature is a fundamental element in meteorology. The surface of the earth derives its warmth almost entirely from the sun. The rays of light and heat which emanate from the sun fall upon the surface of the earth, causing an increase in its temperature. As there are great differences in the nature of the earth's surface, there are consequently great differences in the warming effect produced. Land, for instance, heats up very rapidly, while water becomes warmed much more slowly. The air is not heated by the passage through it of the sun's rays, but by contact with the surface of the earth. The land and water surfaces communicate their heat to the air lying above them, and so in summer and at midday, the air over the land will be much warmer than that over the neighboring ocean. But, on the other hand, the water does not part with its heat so readily as does the land, and therefore in winter and at night, the air over the land is generally colder than that over the ocean. The atmosphere is, as we have already stated, a mixture of gases, and all gases possess certain properties in common. When heated, gases expand in volume, and when cooled, they contract. If a gas is expanded, or, in other words, if its volume is increased, it becomes cooler, and if compressed, its temperature increases. And if the pressure of one portion of a gas increases, there will be a flow of gas towards the other portion which is at lower pressure, and in the case of our atmosphere this transference of air is made very evident to us as wind. Now if the air over one part of the earth's surface becomes heated to a higher degree than that over surrounding parts, the heated air will expand, and in doing so it causes the air layers above it to become compressed. These layers will then have a greater pressure than the surrounding air at the same levels. A flow of air, therefore, takes place towards the region where pressure is lower, and this additional air will, in turn, compress the air in the layers below it, so that now there will be greater pressure in the surface air surrounding the heated area, and the air at the surface will commence to move towards the heated area from all sides, and a circulation will thus be established, with the result that a wind will blow. A rough illustration of a circulation is found in what happens when a window in a heated room is opened top and bottom. The warm air will flow out at the top, and cooler air will flow in at the bottom to replace it. Small local atmospheric circulations are found everywhere, and every day, all over the world, but, because the sun's heating power is so very much greater in equatorial regions than elsewhere, and because in higher latitudes the sun's altitude in the heavens varies considerably during the course of a year, it follows that great seasonal changes of temperature must occur, and also that great seasonal circulations are set up in the atmosphere like great currents in the ocean, and these great seasonal circulations dominate the weather and its changes. Section 4. The effects of turbulence in the atmosphere. The turbulence that takes place within the lower layer or troposphere is much too complicated to describe in detail, but its broad features are indicated in the general circulation of the wind and the distribution of pressure and temperature on the earth's surface. Along the equator there exists a belt of calms, called the doldrums. This belt is the mainspring of the great atmospheric currents, for here the maximum effect of the sun's heat is felt. The heated air is rising and overflowing in the upper regions. To take the place of this rising air, a further supply flows in from north and from south, and this supply comes from the neighbourhood of the tropics of Cancer and Capricorn respectively. Now these winds are moving over a globe rotating on its axis, and a curious thing happens to the winds on account of this rotation of the earth. Every passenger who has boarded a tram car as it is turning a street corner has experienced the sensation of not being able to walk straight along the car, but being thrown to the side instead. The reason is that the passenger tends to keep moving in the direction of which he began, but the car is twisting beneath him. So it is with the wind, which moves over the earth's surface above or below the equator. The earth's surface is twisting beneath the wind, and thus the wind appears to become deflected from its original direction relative to the surface of the earth. The air which surrounds us is, in a word, being carried along with the revolving earth, just as the passenger is being carried by the car. But as the wind can move independently of the earth, or the passenger independently of the car, a change in the direction of the latter produces an apparent change in the direction of the former. In the northern hemisphere the deflection is to the right, and in the southern hemisphere to the left. The trade winds. Therefore, the winds moving southward and northward towards the equator become deflected, and are found blowing from northeasterly and southeasterly directions respectively. These winds are called the northeast and southeast trades, and are remarkably constant winds. Now the air that has risen at the equator moves out towards north or south above the trade winds, and for the reason above mentioned its direction becomes southwest or northwest. These upper winds are known as the anti-trades, and they descend slowly in the regions of the tropics, where there exist other belts of comparative calm called the horse latitudes. To the north of the Tropic of Cancer there is a main drift of surface wind from the southwest, while in the southern hemisphere there is a similar surface current from about west-northwest in the corresponding region. In the upper air these directions become more nearly westerly. In the southern hemisphere these winds are so well established as to be known as the roaring forties, but in the northern hemisphere they are not so definite in direction. This is due to the predominance of sea in the southern hemisphere, whereas in the northern one the land and sea areas are more equally divided. As already mentioned, land and water surfaces behave very differently under the influence of the sun's heat. Land becomes rapidly heated and cools with great rapidity. Water is slow both to get heated and to lose its acquired heat. In summer we find areas of high pressure and low temperature over the oceans just north of the Tropic of Cancer and south of the Tropic of Capricorn, while areas of low pressure and high temperature exist over the great continents. When winter comes, the high pressure with intense cold is found on the continents, while the sea is now the region of warmth and low pressure. These seasonal variations are much more strongly marked in the northern hemisphere than in the southern one. Section 5. The Indian Monsoon. One very important effect of the seasonal change is to be seen in the monsoon, which occurs with wonderful regularity every year over India. During the winter, the winds blow over this country from the northeast. These winds are blowing outwards from the region of high pressure that then covers all the northeast of Asia. The winds are therefore cool and dry. But with the arrival of summer, the Asiatic high pressure gives way to a general low pressure distribution, the center of which lies over Persia and Baluchistan. At the same time, a region of high pressure is found in the southern Indian Ocean between Madagascar and Australia, and the air which moves from this high area towards the low center will in the northern hemisphere be deflected to the right, as already explained, and so will have a southwesterly direction instead of a southerly one as it approaches the Indian coast. This air has been travelling over a wide expanse of equatorial ocean, and therefore contains a vast amount of moisture in the form of water vapour. When the wind arrives at the west coast of India, it encounters there the long ridge of mountains that runs all down the Malabar coast, and the mountains become a barrier which the wind has to surmount before it can continue its course. The air is therefore forced upwards, its pressure is decreased. Thereupon it becomes cooled and can no longer retain the water vapor that was easily held by the warmer air. The capacity of warm air for water vapor is very much greater than that of cooler air, and if air is cooled, any surplus of water vapor is forced to condense out as cloud, and eventually as rain. Thus it is that the southwest monsoon wind brings torrential rain to the west coast of India. Similarly, the air streaming up the Bay of Bengal meets with mountain barriers in southern Assam and along the Burmese coast, and here again the rainfall is terrific. The moisture still remaining in the air is brought down finally on the southern face of the Himalayas, when the air encounters that mighty mountain wall, and this region also has heavy rain. It is believed that Cherrapunji in southern Assam has the heaviest rainfall in the world, nearly 500 inches falling in a year. Section 6. Recording Methods. The organization of a meteorological service. In countries possessing an official meteorological service, the general plan adopted is that of a central office where the forecasts are prepared and issued and the statistics dealt with, and with this central office there is associated a large number of observatories, telegraphic recording stations, and climatological stations, all of which deal in greater or less detail with the recording of the meteorological elements. The observatories and telegraphic reporting stations take simultaneous observations at certain definite hours, and transmit these observations immediately in code by telegraph to the central office, where all the observations so made are plotted upon a map of the country, and from the map so drawn, certain inferences as to the probable course of the weather are made by the staff whose duty it is to prepare the forecasts. In this country, the hours for sending these telegraphic reports are 7 a.m., 1 p.m., and 6 p.m., and at some stations also at 1 a.m., all times being Greenwich Mean Times. The observations usually sent are those of pressure, temperature, wind direction and force, humidity, visibility, sunshine, rainfall, cloudiness, general character of the weather, and certain other more technical details. In order to obtain these data, the more important stations are equipped with a considerable instrumental installation, while at the smaller stations some of the observations, such as those of wind force and direction, are made by personal estimation, in which a very high degree of accuracy can be attained by an intelligent and painstaking observer. Recording instruments. The instrument used for recording pressure is a barometer, which in its standard form consists of a glass tube about 36 inches long and 1/4 inch or 1/2 inch in diameter. The upper end of the tube is closed, while the lower end is open and dips into a cistern containing mercury. The tube is first of all filled completely with mercury, and the open end is carefully covered, as, for example, by the finger, so that no mercury can escape from, nor air enter, the tube. Then the tube is inverted and the open end immersed in the cistern of mercury. If the finger is now removed, the mercury in the tube will be seen to fall until the top of the column stands somewhere about 30 inches above the level of the mercury in the cistern, and the space that is left between the top of the mercury column and the upper end of the tube is an absolute vacuum. The column of mercury in the tube is prevented from running out completely by the pressure exerted by the atmosphere on the surface of the mercury in the cistern, and this implies that the weight of the mercury column must be exactly balanced by the weight of a column of air of equal cross-section, but extending from the surface of the mercury in the cistern up to the absolute limit of the Earth's atmosphere. Therefore, when we talk of the rising and falling of the barometer, it means that the length, and therefore weight, of the mercury column is increasing or decreasing, and that the weight or pressure of the counterbalancing air column is changing sympathetically. In other words, in the barometer the pressure due to the weight of mercury is equal to that exerted by the atmosphere. Photography used for recording purposes. In the chief observatories a simple barometer is mounted in an ingenious form of camera, and a continuous photographic record of its fluctuations is obtained upon a sheet of bromide paper mounted on a cylinder, which is rotated by clockwork. The record thus obtained is called a barogram, and is amenable to the most accurate measurement, its tabulated readings forming a basis for statistical analysis of pressure variations. Another instrument used for recording pressure is the aneroid, which consists essentially of a small, thin, circular corrugated metal box, from the interior of which the air has been exhausted, thereby forming a vacuum within the box. The air pressure acts upon the sides of the box, causing them to yield or to recover against the action of a spring, and by a system of levers these movements are communicated to a hand which moves over a dial upon which a scale is engraved. The aneroid is a convenient and portable instrument, but is much less sensitive and accurate than the mercury barometer, is in the form of the familiar barograph, an instrument wherein 8 of these small vacuum boxes are superposed, and their combined movement is magnified by a system of levers and transmitted to a pen, which then traces a record of the movement upon a paper chart mounted upon a drum actuated by clockwork, and making usually 1 revolution in a week. The temperature of the air is recorded by means of thermometers, instruments whose appearance is very familiar to everyone. A thermometer consists of a glass tube having an extremely narrow bore, which is enlarged at one end into a bulb, either spherical or cylindrical in shape. The bulb is filled with mercury, which likewise fills part of the narrow bore in the stem of the thermometer. If the temperature increases, the mercury in the bulb expands and the column in the bore rises, while a cooling of the air causes contraction of the mercury and a decrease in the height of the column. The Stevenson Screen. Meteorological stations are equipped with a set of thermometers for recording various facts regarding the temperature. The instruments are housed in a box of special design known as a Stevenson Screen. This is usually about 20 inches wide from east to west, 13 inches deep in the north-south direction, and 14 inches high from floor to roof inside measurements. The roof is double with an air space between, and the sides of the box consist of a double set of louvers, while the bottom also is so constructed as to provide free ventilation to the thermometers within, though at the same time preventing sunshine from falling upon them. The screen is placed over grass at a height of 4 feet, and the site is so chosen that it shall be as open as possible to ensure the true atmospheric temperature being recorded. The screen and stand are always painted white both inside and outside, as a further precaution against the effects of the sun's heat. Inside the box there are usually mounted 4 thermometers, 2 of the ordinary pattern in a vertical position on a frame. One of these has its bulb covered with thin muslin, which is maintained always in a damp condition by water which is drawn by capillary attraction along some threads of cotton wick from a water vessel kept beside the thermometer. These 2 thermometers are known as the dry and wet bulbs respectively. The dry bulb registers the actual air temperature, while the wet bulb gives a reading somewhat lower. This is due to the loss of heat caused by evaporation taking place from the wet muslin, and the difference in temperature between the bulbs is greater in dry weather than in damp, because evaporation is much more rapid when the air is dry. Consequently, from a comparison between the readings of the 2 thermometers, we can obtain the degree of moisture of the air, or the relative humidity, as it is termed. In foggy weather there is little or no difference between the 2 readings, but in showery weather there is often a considerable difference, so that, even though rain may be falling, it does not necessarily follow that the air is damp. On other frames, but arranged horizontally, are 2 other thermometers of somewhat different pattern. These are used to determine the highest and lowest temperatures that have occurred during any particular period, and are known as maximum and minimum thermometers. End of section 15. The Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Outline of Science, by J. Arthur Thomson. Meteorology, Part 2. Section 7. Wind Recording. For obtaining records of wind force and direction, the standard instrument now employed is the pressure tube anemograph, invented by Mr. W. H. Dines, F.R.S. There are some slight differences in detail in the more recent models, but all patterns work on the same general principle. A steel pole, varying in height between 15 and 80 feet, according to circumstances, carries at its top a movable vane which is really an open tube, the mouth of which always faces the wind. By means of a system of connecting pipes, the wind pressure at the mouth of the vane is transmitted to the recording part of the instrument. This consists essentially of a hollow, water-borne float to which a recording pen is attached. The change of wind pressure causes the float to rise and fall, and so moves the pen over the chart. The pen pulses up and down with every fluctuation of the wind, and the record obtained shows a broad ribbon-like trace, the middle of which gives the average velocity of the wind, while every single gust is recorded. In gales, the average wind velocity may be about 50 miles per hour, but the individual gusts may reach to over 80 miles, while the lulls may sink to about 20 miles. The highest gust yet recorded in the country was of 110 miles per hour at Quilty during the storm which swept northwards across Ireland on 27th January 1920. In addition to the velocity and gustiness of the wind, this anemometer records also the direction from which the wind is blowing. The movements of the vane are transmitted by an attached rod, which passes through the hollow pole support directly down to the recording part, where the variations of direction are traced on the same chart just below those of the velocity. An older form of recorder, the Robinson cup anemometer, gives a record only of the mileage run by the wind in an hour. The Robinson anemometer is also fitted for recording direction as well as velocity. Rain recording. The rain that has fallen during any period is registered by collecting the rain in a gauge, which is simply a funnel of circular cross-section with deep edges. From this funnel the rain runs into a collecting vessel, and is measured in a glass graduated to read in hundredths of an inch, or in tenths of a millimeter. The gauges or funnels are usually of either 5 or 8 inches in diameter. A more detailed record is obtained by the hyetograph, or self-recording rain gauge, of which there are many patterns, most of them registering by the action of the weight of the water collected from the gauge funnel into a floating vessel to which a pen is attached. When this vessel becomes filled with rain, the pen is at the bottom of the chart, and an automatic siphon comes into action, emptying the vessel and preparing it for further recording. Sunshine recording. The instrument for registering the duration of sunshine is the Campbell-Stokes sunshine recorder. It consists of a metal frame forming half of the central zone of a sphere. Within the arms of this frame there is placed on a small pillar a sphere of glass which acts as a universal lens, whose focus falls exactly onto the inner surface of the frame. The frame is adjusted to the latitude of the station, so that the focused image of the sun's path is parallel to the edges of the frame, and in the frame are cut 3 sets of grooves to hold specially prepared cards that will char without igniting. Owing to the changing altitude of the sun in the sky as the seasons advance, separate types of cards are used for winter, summer, and the equinoctial periods, and these cards are placed in their respective sets of grooves. Whenever the sun shines, its light and heat are focused exactly onto the surface of the card, with the result that a charred trace is left to record the fact. Section 8. Cyclonic Disturbances. Cyclones and Anticyclones. Cyclones and anticyclones are names familiar to everyone who pays attention to weather reports. They are terms applied to those erratic changes which take place within the great general circulation of the atmosphere, which has been already described. Within the tropics, sudden sharp revolving storms, known locally as hurricanes, whirlwinds, and typhoons, sometimes spring up and cause immense havoc. These storms usually cover a limited area and follow well-defined tracks. The tornado of the United States often leaves behind it a track about 10 miles long and only a few hundred yards wide, but within this track destruction is singularly complete. In our latitudes, however, the cyclonic disturbances are much more frequent and are not nearly so severe, but they cover a much greater area, being sometimes 1,000 miles in diameter. The cause of these disturbances has been stated to be due to the irregular heating of the land, and to the rapid ascent of warmed air in the case of the tropical storms. But for those disturbances in our latitudes, the meeting of 2 great air currents of different temperature has been regarded as the chief cause by some meteorologists. Others believe they are due to changes that take place in the temperature of the stratosphere, the upper layer of the atmosphere. Probably all these causes contribute in some measure towards the production of the differences in pressure that give rise to the violent winds. The formation of cyclones and anticyclones. Now air, as we have seen, tends to flow from high-pressure areas towards low-pressure ones, just as brooks run down a hill to seek the valley. But this air will, in the northern hemisphere, be deviated towards the right by the effect of the Earth's rotation, as already explained, so that a system of large eddies will be set up in the atmosphere, and there will be a tendency for the air to circulate round regions of high pressure in a direction similar to that of the hands of a clock, while round low-pressure areas the direction will be counterclockwise. All our changes of weather are due to these circulating systems, whose names are made familiar in the daily weather forecasts. The low-pressure system, which used always to be termed a cyclone, is now more commonly referred to as a low or a depression. The high-pressure system is spoken of as an anticyclone or high. The anticyclone may be regarded in general as the normal settled weather, while the depression bespeaks bad and usually stormy weather. The cyclonic depressions form and develop chiefly along a belt which stretches from the Great Lakes of America across the Atlantic to northwestern Europe, and they are much more numerous in winter than in summer. It is worthy of note that at this season there is extreme cold in central Canada, while the combined influences of the Gulf Stream drift and the general southwesterly current of wind across the warm ocean maintain a temperature on the coast of Norway fully 25 degrees Fahrenheit warmer than that found in the Gulf of St. Lawrence, about 1,000 miles farther south. Then there is a cold ocean current streaming down past Labrador from Baffin's Bay, and a steady flow of cold air is sweeping from off the ice-clad plateau of Greenland. The temperature conditions are therefore very complicated and very favorable for the development of the depressions. The depressions formed over America move generally northeastward towards Greenland, while those reaching our neighborhood usually commence out on the Atlantic, and either skirt our islands in a northeasterly direction towards northern Norway, or move across them on an easterly course to the Baltic. Let us see what happens when one of these depressions passes over our islands. For the purpose, we will assume that for some days there has been a spell of fine quiet weather, with cloudless sky and a steady high barometer all over the country. Then, one morning, the observers at the stations in the west of Ireland see a few slight traces of mare's tail cirrus cloud low down on the western horizon. Gradually these clouds, which are 5 miles high, move up from westward till they are overhead. Behind them the lines of cirrus become denser, and eventually close up into a complete thin cloud sheet, in which there may be seen a halo round the sun. Meanwhile a wind has begun to blow from the southward, and on examining their barometers the observers see that a fall has now commenced, which is slow at first, but which, as time goes on, becomes faster. The sky is now covered with a sheet of heavy leaden grey cloud, in which a watery sun can be seen dimly shining. This cloud is called Altostratus. It is only 1/2 as high as the cirrus seen before it, and this means that water vapour is condensing out of the air in increasing quantity. Time passes. The barometer is now falling rapidly, while the southerly wind is blowing with increasing force, and still lower cloud of the nimbus type has formed, and from it rain has begun to fall. The wind continues to blow harder till it reaches a gale or even storm force, that is, from 40 to 70 miles an hour, and rain falls more heavily. But presently the fall of the barometer begins to slacken, and then ceases, while the wind becomes lighter and rapidly changes from south to southwest, and then swings rather suddenly into the west or northwest. At this moment the barometer begins to rise, and either then or shortly afterwards the rain ceases, and in the west the sky commences to clear. The northwest wind is now blowing almost as strongly as did the southerly one, while the barometer is rising fast and the sky is clearing rapidly. Some squalls and showers may occur, but soon all is fine weather once more. It is, however, noticeable that the northwesterly wind is considerably cooler than the southerly one that preceded it. Why should this be the case? The theory suggested by the famous Norwegian meteorologist Bjørknes is that in a cyclonic depression there are two main streams of air that converge upon each other. One of these is a southerly current, warm and moisture-laden from its passage over the Atlantic. The other is a cold, dry polar current from the Arctic regions. They meet, and the warm air, being lighter than the cold, is forced to rise over the latter, and in doing so carries up with it the water vapour it contains. The warm air, being thus forced up to a higher level, has its pressure decreased, and therefore becomes cooler, as has already been described, and its water vapour is condensed into cloud, and finally falls as rain, because cold air cannot contain as much water vapour as warm air can. If the sequence of weather changes occurs in the order just described, an observer may know that the centre of the depression has passed to the north of his station, but should the cyclone centre be to the south instead, the observer would experience a less marked difference in temperature. He might probably have more rain, and the wind would shift in the other direction, becoming first easterly, then gradually northerly, and finally northwesterly. Our wet west coasts. The mountain chains in our islands form a barrier to the wind and cause a forced rising of the air, which is attended likewise by the formation of cloud and rain. That is why our west coasts are wetter than our east coasts. Firstly, they are more mountainous, and secondly, they are exposed to the moist, warm ocean winds from the westward and southwestward. Section 9. Clouds. The water vapor that is evaporated into the atmosphere manifests itself in many forms other than rain. All the clouds are due to it, for they are nothing but aggregations of excessively minute droplets of water or crystals of ice that have condensed out of the air because the latter has become too cool to retain them in the form of water vapor. Our skies are seldom without a cloud. We watch them with ever-fresh wonderment and curiosity. The forms of clouds are endless and ever-changing, but there are certain characteristics which allow them to be grouped roughly into several classes. There are the thin, feathery lines and bands of cirrus, commonly called mare's tails, floating nearly 5 miles high. These are formed of ice crystals and give rise to many beautiful sights in the sky, such as the wide rings round sun and moon, called halos. Somewhat lower are the speckled, mackerel, and dappled skies of cirrocumulus and altocumulus, the most beautiful of all clouds. We see a wonderful arrangement of orderly and serried ranks. Between broad, straight, parallel bands of snowy white cloud, we have a multitudinous sea of little wavy, rippling cloudlets. These often show close rings of rainbow colors, coronae, round sun and moon, and they are generally seen during a spell of fine weather. In place of these types, there is sometimes seen the watery sky, known as Altostratus, a greasy gray sky with a patch of pallid light where the sun or moon may be dimly showing. This sky usually follows after the appearance of mare's tail cirrus in front of a depression, and is practically always succeeded by rain. Thunderstorm and hail. Lower still, about a mile high, we see the great rolling masses of clouds heaped up in the sky, which are called the cumulus, the ordinary domed woolpack clouds of the summer sky. They are the dark clouds with a silver lining. The cloud is due to moisture carried upwards by ascending air currents which have been warmed by contact with the ground. Here we have also the heavy grey ragged pall of nimbus, the rain cloud. The gigantic cumulonimbus, or thunder cloud, may sometimes grow till it becomes 3 miles deep from summit to base. It is simply a dense rain cloud of the cumulus form. It is very unstable, and is the source of all our heavy showers of rain and hail in the summer months. Often it is accompanied by storms of thunder and lightning, the latter caused by the disruptive discharge of the electricity that is accumulated upon the raindrops in the cloud, and the former being the audible effect of the discharge. Light travels nearly 1,000,000 times as fast as sound, and therefore we see the lightning before we hear the thunder. Both are, of course, actually simultaneous. Lightning flashes may take place between cloud and earth, and also from cloud to cloud. There are many clouds in other parts of the world which we have not portrayed here. There is not always a simple answer to the question, why they do this and why they do that. The huge cloud which overhangs a volcano, Humboldt's volcanic cloud, as it rolls in huge masses, with the lightning flashing through it, sometimes descends to earth with violence, and rolls down the mountainside with a velocity for which neither gravitation nor wind can account. It so moves because it is attracted to the earth by the direct action of its high electrical charge. In various degrees, similar electrical phenomena doubtless play their part in the movements of more ordinary clouds. Again, the gossamer threads of cirrus clouds, the highest clouds of all, sometimes run criss-cross in complex entanglement, and do other things which wind or wind alone is not enough to account for. The puzzles which the clouds set us, one way and another, are endless, and our study of them, like that of so many other interesting things in the world, has only begun. The formation of clouds is not easy to explain. To do so requires on the part of the reader a knowledge of the laws of thermodynamics, and these are rather complex. But anyone can observe the clouds intelligently, and the changes they undergo, and from these changes learn to anticipate the weather that is likely to follow. Such a study will be found as interesting as it is useful. The cause of mists and fogs. When warm air blows over cold sea, the air becomes chilled in contact with the cold water. The water vapor in the air then condenses out as fog, which is thus really a layer of cloud resting on the earth's surface. In somewhat similar manner, the rapid cooling of the land on a clear night gives rise to valley mist and dew. In winter time, when condensation takes place below the freezing point, we have falls of sleet or snow in place of rain, and hoar frost instead of dew forms on the ground, while a warm wind setting in suddenly after a hard frost may cover trees and walls with a glassy coating of ice. Large hailstones, if examined, often prove to be built up of several distinct layers of ice, due to the fact that they are carried up and down many times by the powerful vertical currents of air in the cloud from which they fall, and by this process they receive successive additions of water which become frozen when the hailstone again reaches the higher regions of the cloud. The atmosphere everywhere contains dust in suspension. Sand blown from the desert, salt from the ocean spray, soot from factory chimneys, ashes hurled from volcanoes, the debris of meteorites, and pollen from the flowers all contribute to form the veil that lies between us and the sun. Were it not for these dust particles in the atmosphere, we should never see those gorgeous colour effects that delight the eye. Our azure skies would be almost as black as they are at night, and we should see the sun and stars shining with undimmed lustre, for it is really the dust that produces the lovely limpid blue of the sky. The floating dust particles are exceedingly minute, especially those found in the upper air. They scatter the blue light rays from the sun, and thus cause the sky to assume the colour that it does. The colour in the clouds, the aurora. The soft, shimmering light of twilight is merely the lingering illumination by the sun of the dust particles in the higher regions of the atmosphere, and the many beautiful spectacles seen at sunrise and sunset are also due to the diffraction and scattering of the light rays from the sun. The dust particles and water droplets in the atmosphere have the power of scattering first the blue-violet and then the green components of white light, and so causing the light to change through yellow into red. The glorious tints of the rainbow are due to the reflection and refraction of the rays of light from the sun by the drops of rain, which act like tiny prisms and break up the white light into the rays of varied colours of which sunlight is really composed. But no appearance in our skies can vie in mystery and delicate beauty with the aurora, whose shimmering rays of yellow-green, rose, or crimson light at times transfigure the starlit skies of winter. The aurora occurs some 50 miles up in our atmosphere, and is generally regarded as being due to electrical rays of the nature of the cathode rays which are given out by the sun in greatest quantity at the times of sunspot maxima. The frequency of aurorae, of sunspots, and of magnetic storms within the earth show a sympathetic connection with each other, and are, in all probability, due to the same original cause. Contrary to general belief, the aurora does not presage stormy weather. Section 10. Periodic Variations. The question is often asked whether our weather is changing for the worse, and to this the answer is in the negative. Very slight variations in temperature and in raininess are known to recur in some places and to have some agreement with the sunspot cycle of about 11 years, and there have been alternations from dry and warm periods to cool and wet ones, but the periods are very irregular and the changes slight. The factor that does really make a difference to our weather in Britain is the average position of the cyclone track during the year. If the track is more northerly than usual, and passes to the north of Scotland, the year will be brighter, drier, and warmer than normal, because our islands will then lie more under the influence of the Atlantic high-pressure system. But if the cyclone track lies more southerly than is its wont, we shall have duller, colder, and wetter weather than usual. And very often an abnormal season is followed by one of opposite abnormality. The amazing summer of 1911, with its halcyon days, was followed by the dull, cold summer of 1912, while the very cold December of 1879 over Europe was succeeded by the mild December of 1880. In Central Europe, the difference of temperature between these 2 months was over 20 degrees Fahrenheit. It may therefore be said that the chief characteristic of our weather is rapid variability rather than slow periodic change. Weather lore. A good deal of traditional weather lore is familiar to most people, and part of it, at all events, has some scientific basis. There are certain cloud developments, such as those associated with the Depression, and which have been already described, that are really accurate guides to coming changes of weather, and there are many reliable maxims in use by sailors, as for instance, "If the wind backs against the sun, trust it not, for back it will run," a saying that is quite justified by the behaviour of the wind before a coming cyclone. Such proverbs are based on experience and are capable of scientific explanation. Another adage, that "a rainbow in the morning is the shepherd's warning," is also accurate, for it implies that if showers are falling as early as morning time, they are likely to continue most of the day, and this is very likely to be the case, for the rising air currents that form the shower clouds are not usually effective enough to cause showers until the afternoon. Therefore, if showers are already falling in the forenoon, they are not likely to cease before evening, and may even continue to fall during night time. Halos round the sun and moon are in the majority of cases followed by stormy weather, because the cloud sheet of ice crystals, in which the halos are produced by the refraction and reflection of the light rays by the crystals, is always found in front of a depression, though it may also occur without the presence of a depression. Other maxims, again, have considerable value in some localities, but are inaccurate in others. In mountain districts, the cloud cap that forms on the mountain tops is often used as an indication of the coming weather. Statements regarding the stormy presage of a red sky in the morning, or of the happy augury of a grey dawn, are not always trustworthy, for their accuracy depends entirely upon the meteorological situation, and a good deal of expert knowledge is required before such signs can be correctly interpreted. But, on the other hand, some proverbs are quite unworthy of serious attention. The effect of the new moon upon the weather, so widely believed in, has been investigated and found to be non-existent. The belief that 6 weeks of daily rain will follow a wet St. Swithin's Day is equally absurd, for the common occurrence of more frequent rain after that date is due merely to the seasonal change, from the dry early summer to the much wetter late summer and early autumn, to which our islands are subject. But the old maxims provide a very interesting study, as those can testify who have read the volume on weather lore compiled by Mr. Richard Inwards. End of section 16.